Welcome back to week 7 of pre-calculus. Our second topic this week is logarithmic functions. Because logarithmic functions are tightly related to exponential functions, let us recall a few facts about exponential functions. If we have a function of the form b to the power x, where b is positive and different from 1, such a function is called an exponential function. The graph of such function looks in one of two ways. When b is greater than 1, this is a very rapidly increasing function. And when b is between 0 and 1, this is a rapidly decreasing function. Either way, this function is injective. It maps different x's into different y's. It's easy to see from the picture. In the left picture and also in the right picture, we see immediately that whenever x1 and x2 are different, so are the corresponding y's. F is injective on its entire domain, which is the interval from negative infinity to infinity, or simply R. And again, injective means that x1 not being equal to x2 implies f at x1 is not equal to f at x2. Now, what about the image of this function? The image, in both cases, whether b is greater than 1 or less than 1, the image in both cases is the set of positive real numbers. And if now we consider this function from the set x to the set y, where x is R and y is the set of real numbers that are strictly greater than 0, we have this function both injective and surjective. The image equals the codomain. Remember, surjective means the image of your function equals the codomain. F is injective and surjective, and therefore bijective. Being bijective, it has a unique inverse function. How do we construct this function? Well, we're going to fix a y anywhere in the set capital Y. In other words, we're going to fix a y which is a positive real number. And whatever x corresponds to that y will be the value of the inverse function at y. That number is called the logarithm of y base b. Here is the formal definition. given a positive real number y and a positive real number b, the logarithm of y base b is the unique solution of the equation b to the power x equals y. Right, so we consider the curve b to the power x. Here, of course, we need to add that b is greater than 0 and b is not equal to 1. So when we consider the curve b to the power x, it will intersect exactly once with any horizontal line that is above the x-axis, and the x-coordinate of that unique point where the curve b to the power x intersects with the line y equals b, the x-coordinate of that point, that distance, is called logarithm of y base b. In other words, logarithm of y base b is that exponent that base b needs to be raised to get y back. When b is raised to the power logarithm y base b, we get y. Logarithm is the function inverse to the function b to the power x. Log x base b is inverse, is the inverse function with respect to the function b to the power x. As we know, there's a close relationship between the domain and range of a function and its inverse. So, for example, we know that the domain of the function b to the power x is the entire real line, and so immediately the entire real line is the image of the logarithmic function. Likewise, by construction, the image of the function b to the power x is the set of all positive real numbers, and automatically this is also the domain of the logarithmic function. So the relationship is very simple, just like with for every function f and its inverse, we have f inverse of f equals x, f inverse of f of x equals x for every x in the domain of f, and also f of f inverse of x equals x for every x in the domain of f inverse. And again, it's important to remind ourselves that the domain of f here is the image of f inverse, and vice versa, domain of f inverse is the image of f. So from here we get immediately these two formulas, that log base b of b to the power x is x. And also that's the realization of this formula. If f is b to the power x, then f inverse is log base b. So when I apply f inverse to f of x, I get x. And the realization of this other formula, f of f inverse of x, is that b to the power log x base b is x. Now it's important to write restrictions for x in each case. So this formula remains true for any x for which this makes sense, which is the entire real line. So I could say x runs over all of R. And this other formula is true for whatever makes sense. Log is defined for positive reals only. So here x belongs to R greater than 0. Let's play with some numerical examples. Compute, for instance, log of square root 6 base 6. So the question being asked here is, to what power 6 needs to be raised? What power do we need to raise 6 to get square root of 6? Well, because square root of 6 is 6 to the power 1/2, we clearly see that 6 needs to be raised to the power 1/2. And so log root 6 base 6 is simply 1/2. Likewise, because 3 to the power 2 results in 9, we see immediately that if we look at the function 3 to the power x and look at the line y equals 9, they will intersect at the point whose coordinates are 2, 9. So the x-coordinate of that point, 2, is the value of logarithm of 9 base 3. Logarithm of 1 million base 10. Well, million is 10 to the power 6. So logarithm of 1 million base 10 is simply 6. And logarithm of 25 base 5 is simply 2, because 5 squared is 25. We should be able to translate exponential expressions into logarithmic, given that the two functions are inverses of each other. For instance, what does the fact that 2 to the power 3 equals 8 tell us? It tells us that 3 is logarithm of 8 base 10. Correct? If we look at the curve 2 to the power x, our favorite, and compute the value of that function at 3, the y-coordinate will be 8. So 3 is logarithm of 8 base 2. Likewise, the fact that 5 cubed is 125 means that logarithm of 125 base 5 equals 3. Look at this one. 10 to the power negative 4 equals 1 over 10,000. So we're looking here at the curve 10 to the power x. And what this says is that at the point negative 4, the corresponding y value is 1 over 10,000. So that means negative 4 is that power that 10 needs to be raised to get 1 over 10,000. In other words, negative 4 is a logarithm of 1 over 10,000 base 10. And likewise, the last expression, 2 to the power negative 1 equals 1/2, simply states that logarithm of 1/2 base 2, the power to which 2 needs to be raised to result in 1/2, is negative 1. All right. There are two special types of logarithms that I want to mention. The only requirement to base b in a logarithm is that b be positive and different from 1, the same as the requirement for a base in a logarithmic function. Excuse me, the same as the requirement for a base in the exponential function. So technically, you can use any bases you want as long as they are positive and different from 1. But there are two special bases that are used very often. One such base is the special number e that we learned when we were talking about computing interests with compounding. Remember, e was defined as the limit of the expression 1 plus 1 over n to the power n. N goes to infinity. That special number e, which is roughly 2.71828, is definitely positive and greater than and different from 1, positive and different from 1. So nothing prevents us from considering logarithms with that base. They're given special notation. Instead of log x base e, we will write simply ln x. N is for the word natural. Logarithms based e are called natural, which seems a little bizarre because at first this choice seems all but natural. It, for instance, is very hard to say what natural log of 2 is. What is this as a number? Well, it's some irrational number, which is hard to compute. And at first, this choice seems all but natural. But when you get to calculus or differential equations, you will learn that this choice is in fact very much natural for many reasons. Somewhat more natural choice is to look at logarithms base 10. These are called common logarithms. And they are given special notation LGX. So whenever you write LG, you don't need to write base anymore, and everybody understands that the base is 10. So this finishes this introductory piece about logarithmic functions. Again, to summarize, the logarithmic function is the inverse of the exponential function. Given the function b to the power x, where Of course, we assume that b is positive and different from 1. For every positive b, for every positive y, there is a unique number that the base b needs to be raised to result in y. In other words, if you consider the curve b to the power x and intersect that curve with a horizontal line whose y coordinates are all equal to y, the coordinates of the points of intersection will be, second coordinate will of course be y. The first coordinate will be, by definition, logarithm y base b. It is the number that b needs to be raised to result in y. We have these nice relationships between domain and image of the exponential function and the logarithmic function. And of course, we have these two formulas that are utterly important. All right, next we will talk about graphs of logarithmic functions. Thank you.